Good evening, everyone. It's an absolute pleasure and honor to be in Copenhagen today and to be talking to you. I'm really excited and thrilled to be invited to speak at Science and Cocktails. So many of you don't know, but I've had a long association with Copenhagen. I actually had a professorship, the Sophia and Tycho Brahe professorship at the Niels Bohr Institute when I was a junior professor at Yale. And I used to come here regularly and absolutely in love with Danish design. So I can talk endlessly and listen endlessly about architecture and design. And anyway, it was such a lovely day today, so I'm thrilled to be back. But back to what we have to do today. I have to share with you all these exciting discoveries that have been tumbling out every day, literally every day. There's a new discovery about black holes from the James Webb Space Telescope. So let me start out by telling you a little bit about sort of this human. Why is it that not just me, but you are obsessed with black holes? What does it have? There's something about black holes that draws us all in. And in fact, I want to tell you that actually it's a very fundamental human impulse, wanting to know who we are, where we came from, and what is going on in this cosmic drama with galaxies, stars, the night sky. And it started very early for human beings. It really started the first evidence that we have for human beings having stood up in the night sky and actually recorded it. Obviously, the first human Neanderthal looked up in awe, but didn't quite record it. The first recording is the Nebra sky disk that was found in the Saxony-Anhalt region in Germany. And it has a depiction of the sun, the moon, the Perseus cluster, and we have no idea what they were doing documenting it. What did they use it for? But then, as we go on in time, we see with the Mesopotamians, with the Venus sky tablet. So they had many of these sort of cuneiform tablets. This one marks the positions of the planet Venus over time. So they were tracking the orbit. So this is super remarkable. Not only did they know that Venus was a planet, but they were trying to follow the orbit. But guess what? At this time, people were not really looking for the kind of scientific explanation or understanding that we're going to go through today with black holes. They were really looking for correlations between the celestial and the terrestrial, right? So there were floods, there were things happening on Earth. They just wanted to make connections. And this whole idea of there may be a reason and an explanation and a cause and an effect that we can connect, that there ought to be physical laws, principles that order the universe, came a little bit later, as you all know. But before we go there, one of the most fundamental shifts in our cosmic thinking really comes from Copernicus, as you all know, who completely shifted the pivot from the Earth to the sun for our solar system. And at this time, our conception of the entire universe was the solar system. We didn't know about anything else beyond our solar system. We, of course, didn't know about the outer planets either. So I am actually, as you probably guessed, slightly obsessed with maps. So I had to sort of throw in a few maps here and there for you. One of my favorites is the Catalan Atlas that I have up there. That's from the 1300s. What is great about that map is that it encodes this shift in the kind of explanation, empirical explanation, that comes to define science itself. So in that map, at the four corners, you see these four beings holding an astrolabe. So an instrument and measurements now become part of understanding the universe, as it turns out. And of course, as you all know, so of course that map I've thrown in again because I love that map, although it's the geocentric universe and not quite. It was well after Copernicus, and this is just to show you that when somebody proposes a radical new idea, there's a lot of resistance. People don't change their mind right away. Even within the scientific community, it takes time. So even after Copernicus shifted the pivot from the sun, moving the sun to the center of the solar system in 1543, Bartholomew, that map, still has the Earth at the center of the solar system. So there was a bit of a lag, but of course, you know how it all turns out. And what is remarkable is where we are with our understanding of a solar system today. So today we have found 5,500 planets around other stars right around in the neighborhood of our own sort of solar system. So that's already telling us that there are probably more planets than stars in the universe. Isn't that mind-boggling? Nobody could have imagined that 35 years ago. Okay, so let's move on to trying to understand how cosmology developed, to tell you something about why black holes are just so enigmatic. So cosmology and astronomy have focused on the visible universe. Why? Because light is our cosmic messenger. We learn everything about the universe because of light, the light that is emanated by objects. So one of the first big sort of shifts where light, i.e. the presence of other galaxies in the universe, was inferred from data was by the astronomer Hubble in 1929. And he came up with this plot of the speeds of galaxies right around us and as a function of their distance. So the farther away a galaxy was from our own galaxy, it was hurtling away from us much faster. This was really peculiar. The only way you could make sense of this observation was to actually admit that the universe was in fact expanding. So this was the first disorienting discovery about our universe. And of course, before he did that, Hubble had to do something else, which is, expand our cosmic view and take us out of our solar system and out of our galaxy. So in fact, he even found sort of the distance to the Andromeda Nebula, which is our nearest neighbor galaxy, which in fact, anomalously, is not moving away from us, but actually is on a collision course with us. But we don't have to worry. We're talking billions of years. We're good. So then, not only was he able to show that the universe was expanding, but there were many, many other galaxies in the universe. Fast forward to today. What do we know? We have moved beyond just understanding the visible constituents of our universe. We have a cosmic inventory that is really remarkable. We know that the bulk of the universe is made of invisible entities. And the invisible entities are dark matter and dark energy. So the majority of matter in the universe is made with some exotic particle that likely formed in the very early universe. We don't know what it is. We know what it does. We know how it manifests in the universe, but we don't know what it is. And the ordinary atoms that we are made of are a tiny sliver of the entire cosmic inventory, and that's like 5%. Everything in the periodic table, everything that we are made of, just mere 5% of the inventory. Everything else, the bulk of the stuff, is another invisible entity called dark energy. Now, that's a story for another day, not today. But what we know now is a really, really sort of precise timeline for the universe. We know when it started. We believe our universe started. And what we mean by the universe starting is we define t equals 0, the start of time itself, when the universe and the time that's elapsed is about 13.8 billion years. So we have a reasonably good idea. Oops, I seem to have butter fingers. Let me go back. What we know is the sequence of notable events in the universe. We know when, most likely, we thought we knew when the first stars formed, and we knew when the first galaxies assembled, and we were able to start making predictions of what a powerful telescope like the James Webb, which was built to peer into the most distant bits of our universe possible at the moment, would start to uncover. And so we had these theories, those were validated by data, and we extrapolated them and said, okay, this is what we should expect in the infant universe. It turns out, of course, that the universe always holds enormous surprises. We already knew that. So we knew that when already we looked at Hubble's discovery of these external galaxies. And then the Hubble Space Telescope actually went and peered at what was a deep look at what was supposed to be a blank piece of sky. There was nothing dramatic going on. It seemed like a very average, very dark piece of sky, except the telescope was now staring at it for a very long time, collecting as much light, sucking in all the faint light. And guess what it revealed to us? It revealed to us millions and millions of galaxies. So the universe can be unseen because we don't have the instruments and the capacity to see it, or it can be unseen because the entity itself does not emit light. And this is where black holes are going to start coming in. So what I'm going to show you now is our state-of-the-art understanding of what dark matter is doing in the universe, how galaxies are forming in the universe, and what role we may believe that black holes may be playing. So I'm showing you slices of a simulation. So this is just isolating the dark matter. So dark matter, as I told you, is the dominant matter in the universe. It's the scaffolding within which all the visible stuff that we see actually gets formed. Dark matter itself does not emit, absorb, or reflect light. It only deflects light. And that's an important point to remember, because that's what black holes are going to do as well. And so this simulation, that was dark matter. And notice that it's aggregating just with gravity. Gravity is the only force in town on cosmic scales. So you saw all that aggregation, and you see these regions that have a lot of those white spots. Those are the regions we are going to form galaxies in. And on the right-hand side, you're seeing the same patch of the universe, but now showing you only the gas. And when I mean gas, it's all hydrogen, pretty much. And so what you see is the way the hydrogen gas is accumulating. We have zoomed into one of those regions. Stars have formed, which are those blue bits. And then a black hole has formed, and that's the red stuff. It's heating up gas in the inner part of a galaxy. And so this, I'm giving you a bit more of a zoom in of how a galaxy would assemble. It would assemble by the sort of accretion, the coagulation of gas, as well as the collisions with a lot of other little galaxies. And you see that dramatically. You see a little galaxy falling in now into this, what's going to become a dramatic spiral. And it already has embedded in its center, at its heart, a supermassive black hole. So the biggest open question, how did supermassive black holes that we are now finding at the center, pretty much every galaxy in the universe, how did they form? Did they form first, or did the stars come first? So these are the big fundamental open questions. But before I take you there to tell you a little bit more about where we are today, I want to talk to you a little bit about the journey. And one of the things that was really peculiar is I've been fascinated with black holes for as long as I can remember. And I found out, and I'm of Indian origin, I was born and brought up partly in India. And I realized there was like an Indian connection to the name and the concept. So it turns out a black hole was an infamous prison where soldiers from the British Army had been left overnight, and sadly, they did not come out of that prison. So it was a point of no return. So it was this property, and this happened in 1756, well before the idea of black holes was really out there scientifically. So it was the concept that there are places of no return, right? This is something I want you to make a note of. What is a black hole then? So I've already hinted that it's going to be some kind of place of no return. But one thinks about the universe and space as a four-dimensional sheet, so space-time. So if space is completely flat, right? There's no matter. Such a universe would have no matter. Why? Because the presence of any matter would cause a divot or a pothole in this fabric of space-time. Just to clarify, this is a four-dimensional quantity, and the way we are rendering it to two dimensions, there's nothing above or beyond, below space-time. Space-time is all there is in the universe. We are all embedded in space-time. The Earth is, the sun is, so on. So the sun causes a little pothole in space-time, so it's a little bump. And any other matter, say a neutron star, which is a little more dense, tightly packed matter, is going to cause a deeper divot. So a black hole, by sort of pushing that same analogy, is a region of space that has the deepest pothole. It actually has a puncture in space-time. Matter is so strongly concentrated that you puncture space-time. And you're like, okay, I don't know what that means. So okay, let's just revisit this. And what scientists often do is when you have a very complex phenomenon, we try to look at it from a bunch of different ways. And then when we do the calculations, we pick the way of looking at it that makes it most tractable, easy to do the computation or the calculation to provide an understanding. Of course, in the end, you have to put all these different views together and you have a composite understanding. So let me start by telling you 3 different ways in which you can really think about black holes, which are actually a place. So they're a place in space-time where the curvature or the actual shape is extreme. Okay, there's a puncture. But one way to think about it, just to kind of connect it to things that we have seen, we have felt, because cosmology and astronomy pose this huge challenge. And this is something that I'm always teased about with my family. I am much more comfortable with solar masses, which is 10 to the 33 grams, than I am with 3 ounces that are needed for something in a recipe, right? I just can't deal with 2 ounces, real kind of concrete stuff that we can measure and feel with our hands. I kind of need this far out numbers. But for those of you who are like me, one way to think about black holes is to understand what I mean by the intensity of the gravity of a black hole. So the strength of gravity is so strong in a black hole that we say not even light can escape it. What does that really mean? Consider the Earth. How many of you have seen launches of satellites, especially SpaceX? Well, there have been many launches, successful launches, but some misses too recently. But we've all seen those launches, right? And you need rocket fuel to push it out of the Earth's grip of gravity. So the attraction of Earth's gravitational force has to be overcome by this rocket to be expelled into space. And to do that, we need to speed it up to about 11.2 kilometers per second. So imagine that's the escape velocity for the gravity of Earth. So just imagine if the escape velocity was actually the speed of light. Nothing material, of course, can move at the speed of light or above. So that's what it really means when we say not even light can escape. So this is like one way to think about it. Of course, the classic astrophysical way to understand what a black hole is materially what it is. And a black hole is the end state. It's the remnant of a massive star. So massive stars that are born with a birth mass of about 8 to 10 times the mass of the sun. They live their life out, explode into a dramatic supernova, and they might leave behind a black hole. So a black hole is also a stellar remnant. It's a stellar corpse that is left behind. And it has intense amount of matter packed into a very, very tiny space. And finally, I've already told you that one of the most accurate, mathematically, physically accurate ways to think about a black hole is as a puncture in space-time itself. And that really tells you something about the extremeness of a puncture, tells you how densely and compactly matter has to be concentrated in a black hole and how intense the gravity, therefore, has to be. Okay, so what's all this song and dance? Okay, now you know what a black hole is. So what's so peculiar about a black hole? You already know that not even light can escape it. Okay, if not even light can escape it, how are we ever going to see these darn things, right? So it turns out that although black holes have this sacred boundary, which is called the event horizon, from which not even light can escape, there are bits, regions around the black hole from which we can get a lot of information. So light, if it gets captured in this region, which is about 1.5 to 2 times the horizon outside, is going to be caught and trapped in perpetuity. It's never going to be lost. And so we will see that light. Okay, that's cool. So basically, what do we need to do? We need to be able to zoom right into the heart of black holes, get as close as we can, and hopefully get to a few times the horizon, and then we should be able to see light from the matter that is being pulled in gravitationally before it reaches the horizon. So we are seeing the matter that's getting heated up, sped up, heated up, that's glowing. And that's what we can see, and that's the principal way in which we detect black holes, aside from the fact that we also measure the strength of their gravity, as we'll see in just a minute. And of course, there are regions beyond, far away from the event horizon. Light will get slightly bent, but it'll go its own merry way, unaffected by a black hole. And you might say, okay, this is interesting. If you think about it for a minute, right? I just finished telling you that the Milky Way, our own galaxy, harbors a 6 million times the mass of the sun black hole in its center. But that black hole, intense as it is, heavy as it is, compact as it is, does not impact us in the solar system. We are far away from the center. We are offset from the center. Why? Because by the time you move beyond 10,000 times the horizon, you move beyond the horizon of a black hole, its own gravity starts to wane. We know that from Newton's laws, right? The farther away we are from a mass, the force of gravity falls off as 1 over r squared. Then what takes its place? Stars. So in our own galaxy, the stars in our galaxy and the dark matter in our galaxy outweigh the black hole by a huge margin, a factor of 1,000,000, okay? So the black hole dominates only right at the center, but as it turns out, it's actually very consequential to the assembly of a galaxy. As I already gave you a hint when I showed you that movie from a simulation. So here is another graphical depiction of what happens to light rays. So you see the black hole there, you see that divot, you see that deep divot, and this grid that you see is sort of space-time, just to show you the stretching and changing of the shape of space-time. So these are all light rays, and you might say, aha, I have seen something like this. Haven't astronomers already detected these light rays that are straying close but are not crossing the event horizon, are getting bent and deflected? And indeed, we have seen that. And you would have seen that. Hold on. An image, okay, it's coming later, of the Event Horizon Telescope collaboration that showed you that donut image. So that was light from outside the horizon that is squirting, that is trapped in there from hot glowing gas. And I told you that that's one way to spot a black hole. The other way, of course, is to look at the gravitational influence. So the gravity of the black hole will influence the inner parts of the galaxy, not where we are, but the inner parts. So this is a zoom in of our own galaxy. And this is data from Andrea Ghez and her group. So she and other collaborators were awarded the Nobel Prize in Physics a few years ago. So what did she do? She and her team, this is real data, mapping the orbits of stars right around the black hole. These are obviously well outside the horizon, right? Because the stars would not have survived. So this is well outside the horizon, still in the region where the gravity of the black hole dominates, and you can see that there is a star whose orbit has closed into a nice ellipse, And that ellipse, closed ellipse, actually gives you the mass of the black hole. Much like the orbits in our solar system, right? So the gravity of the black hole is holding together this stellar system in equilibrium right around the black hole. The other way in which we have detected black holes, you may all remember in 2016, was the reporting of the waves, gravitational waves, that were produced when two stellar mass, the lighter cousins of these supermassive black holes, emitted, that actually caused all of space-time to have a tremor. And that was detected by the LIGO collaboration. And that was, so we've actually found all these multiple different ways to detect black holes. This is the latest inventory of the stellar mass black holes. What you see in blue at the top layer of this chandelier-looking thing are the merged masses of the black holes. And you see these two little blue ones have merged to give you this guy. And that's what we have detected. So we are detecting a lot of black holes via their gravitational waves. So, okay, let's move on to try to understand supermassive black holes, which are my favorite kind of black holes. So these are black holes that are 1,000,000 times the mass of the sun or higher. They inhabit the centers of galaxies. So what's with them? What are they doing? So they are often either fasting or feasting. They're real bingers. So when they are fasting, like the black hole in the center of our own galaxy, there's almost no light, no matter falling in, so no real light coming out. And that's why for our galaxy, we had to look at the impact of the gravity on the stars, because there's no little sort of ring. There's a donut. There was kind of a pinched donut that the Event Horizon Telescope collaboration showed us. There's not a lot of gas there. However, when a black hole is feasting and it is feeding on gas very rapidly, and that gas is glowing before it crosses the event horizon, you see such objects. They are incredibly bright. They're called quasars. And you can see them out into the farthest regions of the universe because they're so bright. They're so bright that they can even outshine a galaxy. So where is a black hole in your average galaxy? So this is a Hubble Space Telescope image. You're going all the way in. And remember, I told you that we can't quite simultaneously get the resolution to go all the way in. So this is an artist's rendering of this gas reservoir, which is like a disk from which gas is getting pulled in by the gravity of the black hole. And so this image shows you something else that you might have wondered yourself. We're all talking about black holes as kind of vacuum cleaners or sucking up matter. It turns out they're not. They're kind of messy eaters. So not everything that's getting pulled in is actually going in. Some of it gets dribbled out. And it gets dribbled out into these jets. So this is an artist's rendering of a jet. But let me show you what the real jets look like. Before that, I want to show you how different wavelengths of light offer us different views of not just black holes, but of galaxies as well. So this is our galaxy seen in different wavelengths. Finally, we are looking into the heart of our galaxy in radio wavelengths. And that's where you start seeing the activity right around the black hole. And that's telling us that the black hole has one other complication that I haven't mentioned yet. They often have magnetic fields that are all tangled all around them that start to show up in the radio emission. So this is the donut that you've all seen before, the Event Horizon Space telescopes on the ground, not space telescope, that actually came up with this remarkable image. One of the other things we know about galaxies that are hosting central supermassive black holes is that the mass of the black hole, which is here, and the mass of the stars in that galaxy are correlated. The bigger the galaxy, the bigger the black hole. So what's going on? How do the stars in the black hole know about each other? Do they know about each other? Are they growing in tandem? So that is one of the big open questions. What is the causation for this correlation that is seen? So that is something that people like me and many other researchers in the field have been working on for a very long time. So let me show you the rendering of a model that we built, because that's kind of the work that I do, theoretical numerical modeling, conceptual ideas turned into models that you can then confront directly with the data. That's the kind of science that excites me the most. And so this is a model that I just showed you, where what you see in those little dots up here, that's the data, that's this correlation, this is the real data. And so any model you build has to eventually account for this, right? So these are the correlations. For those of you who are really into the data and want to know what's really going on with the data, this is the latest data. So these are the correlations of properties of the black hole, the mass, with properties of the galaxy that is hosting them. So, there is clearly something here, right? So this is a fundamental question we have to understand. And if you see the sizes of the event horizons, they actually scale with the mass of the black hole. We knew that already, but data from the Event Horizon Telescope collaboration has really shown us that this is M87 star. It's a monster black hole, 6 billion times the mass of the sun, compared to our own galaxy, where it's 4 million times. So, the difference in the black hole masses translates into a size of the horizon. Then the question is, are black holes always at the centers of galaxies? Or could you have some wandering supermassive black holes? It turns out that yes, you can have some wandering supermassive black holes. And we may have uncovered one such case. This is real data. Remember I talked about the jets, the dribbling of black holes that don't feed very well. So here are some real-life examples. This is data of the jets. So very, very extended jets that are driven, we know, by black holes that are sitting right at the heart of these galaxies. And we also know that there are some times a black hole can aid the formation of stars in a galaxy, although most of the time, they stop the formation of galaxies. They heat up the gas with those jets that prevents cooling and star formation. And therefore, it turns out that black holes played the key role in modulating star formation and hence the formation of a galaxy. So originally, I kept telling you, they are tiny, they're gravitationally very important, just right around the center, but not really that important outside. But it turns out they're really important overall in what a galaxy looks like. Our galaxy is the way it is because we have a central supermassive black hole. And that assembled, and that kind of played with the stars, interacted with the stars, and turned them off, turned them on episodically, and voila, that's where we are now. So we believe that this kind of interplay is very standard in the universe. And there are simulations now in which we can start understanding how this feeding process actually occurs. So these are some simulations, recent simulations, that show you, so what you see here, the black hole is this dot. This is the temperature of the gas, and this is the density, how much gas is flowing in, and you can see the gas flowing in. And this is a zoom out of these showing you, this is that disk, the feeding disk, and I've given you a side view, and the matter is feeding. So this is how black holes grow. They grow by feeding on gas. But they also grow another way, and that is because galaxies in the universe keep colliding with each other. Okay? Galaxies grow by colliding with each other. And therefore, if they have central supermassive black holes, those black holes are going to collide. They're going to collide, they're going to merge, they're going to form a bigger black hole, but they're also going to cause little tremors. They're going to produce gravitational waves. So this is a simulation from one of my former students' work, which he's showing the collision of two spiral galaxies. We are seeing them face on. And the flickering in the center is a black hole that is feeding. If it's feeding, it's flickering. That's the way we've set up this simulation. So you can see when the two galaxies merge, they kind of take a few rounds, they go around each other, then they crash into each other. You produce a bigger black hole in the center. And the thing that you don't see in this picture are the unseen gravitational waves that this collision would produce. So this is another view, a top-down view of how this collision is happening. So here you are seeing top down, you have a big black hole in the center of a galaxy. You have a tiny guy coming in, spiraling and making its way to the center. So this is also a simulation. And so remember I told you the final stage is these tremors in space-time itself from the collisions of black holes. These are yet to be detected for supermassive black holes. To do that, you actually need equipment in space. You cannot do it from the ground like LIGO has done for the stellar mass black holes. Those are in a frequency that is reachable, higher frequencies that are reachable from the Earth, whereas these happen at a frequency that is accessible only from space. So these are simulations. These are all state-of-the-art simulations. So this is a simulation on the right-hand side from a group, a computational group at Rochester. And that movie that I'm showing you took more than 2 years to calculate on a supercomputer, because this takes into account Einstein's theory of general relativity. You can see the grids. You can see how that grid is going to transform and change with the black hole moving. So this is, we've made remarkable progress. And these are breakthroughs that happened within the last 10 years, okay? And even when I was doing my PhD, which was before that, this is not something, this was speculation, and we were all dreaming that this calculation could be done. And this is, of course, thanks to the power of computers, the power of computing, which has grown enormously. So this is another simulation now of the first billion years of the formation of our universe that shows dark matter, gas, stars, and the formation of black holes. So you can see slowly structure emerges. The blue stuff is dark matter. Slowly stuff starts to aggregate with gravity. So there are regions that start out with an initial advantage and some with a disadvantage with matter, so there's fluctuations. And so the bigger fluctuations keep growing. They get amplified over time because more material gets attracted to it, becomes a bigger and bigger heap. And the regions that were devoid of dark matter become deeper wells with less and less dark matter. So the contrast starts to become much more dramatic. The universe starts to become very patchy. And you can see these regions where dark matter filaments intersect. They become very dense. There are regions where there's a lot of matter, and those regions will attract the gas to fall in. The gas will fall in, cool, make clumps, and those dense clumps will become stars. Somewhere in the story, black holes have to form. And the open question about 20 years ago is, where do black holes fit in this drama of star formation, dark matter, gas physics? And that's where the work that me and my research group and some other groups around the world have sort of been doing for the last, 20 years ago, I started thinking about this problem, motivated by the fact, just complete intuition, right? And sort of rebellious by nature, there can't be just one way to make black holes in the universe. There has to be more than one way. And I went about trying to understand if there is physics, if there are physical processes that would allow black holes to form in a multiple sets of ways in the universe. As I showed you, the only way was stellar remnants, stellar corpses. They give you very little tiny black holes, maybe 10 times the mass of the sun, 50 times the mass of the sun. How are you going to make something that is 6 billion times the mass of the sun, starting from something that's 10 times the mass of the sun? Seemed like you would run into problems, and yes, you do run into problems because you start to see these billion solar mass black holes farther and farther back in time as really bright quasars that you are finding. And the time available in the universe to grow is shrinking. So you needed other ways. So that's what motivated our work. So we started looking at it and realized that there was one easy way that you can think of to make a black hole directly circumventing the formation of a star, traditional star, and that is just directly collapsing the gas. Because what's a black hole? You just have to get a lot of matter into a tiny space. Can you do that some other way? We realized in a very early stage of galaxy formation, you could likely do that. They are called massive seeds, heavy seeds, direct collapse black holes. So essentially what happens, something analogous to those of you who've sat in a bathtub, and you pull the plug of the bathtub, and you see the water going in as a vortex really rapidly. Well, assuming that your drains are not clogged, right? It all goes in really fast. Something analogous to that happens in the very early universe. You form these big gas disks that go unstable. The instability is the act of pulling the plug. Something changes, and then the gas gets siphoned down very rapidly. And that way, you can aggregate 10 to the 4 to million times the mass of the sun even in one go. So you can make a black hole whose birth mass is already 10,000 times the mass of the sun. So then the question was, does this happen in our universe, right? So this is, again, sort of a sketch showing you this process, how it could happen. And we worked it out over the years. It took a long time because, the computers were not fast enough and algorithms were not sophisticated enough. And our understanding was, progressing, right? So eventually, in 2017, we reached a point where we were able to outline the entire physics, not only show that it can happen, not only show that it can happen in our universe, but also pinpoint the kinds of places in our universe that have the right conditions for this process to happen. So we were able to show, for example, that if you have a galaxy that formed its first stars, and there was another little piddly satellite nearby that hasn't yet formed its stars, it hasn't cooled enough, then the radiation, the light from the stars that have already formed, will prevent this guy from cooling and forming stars. Basically, you want to prevent the formation of stars so that you give it the opportunity to make all the gas go into a direct collapse black hole. So we were able to show you can do that. When you do that, you get for a brief period of time a really weird kind of galaxy. It's an overmassive black hole galaxy. It's a galaxy whose mass and light are both dominated by the black hole. By matter glowing into the black hole, that light is brighter than the stars. And that's because the black hole itself is very massive. So what I'm telling you is that you can form these galaxies that look like the opposite of our own galaxy very early in the universe. So that's a very clear-cut signature. It's going to look nothing like our galaxy. It has completely different properties. So we predicted that, and we showed. And for those of you kind of interested in, what are the scientists doing? So, make predictions. So the prediction here is, of course, we realized if this happens in the early universe, James Webb should be able to detect this if it happens. It has the capacity. And the reason it has the capacity is because it has eyes that are sensitive to 1 to about 30 microns. So this is in millimeter wavelengths, micron wavelengths that these instruments are sensitive to. And so we predicted that the amount of energy, the light that is coming out, should have this shape. Okay, so there's a sharp rise here and sort of flattening off. And what you see in black are all the limits of what James Webb can see. Anything that's above this black line is detectable. Anything below is not detectable. So all of this should be detectable. So we were able to predict in 2017 this should be clearly predicted and seen. This is just isolating once again to show you that this should be detected. This should be booming. So this data, if such galaxies exist, they should be clearly seen by James Webb. Then, of course, the question is, this is the entire sort of sequence of how you would form this direct collapse black hole, how it would end up giving you this overmassive black hole galaxy. And these predictions were made, fairly sophisticated predictions were made in 2017. And then in 2023, I was sitting in my office, and one of my collaborators, who is an observer, called me, and first he joked, and he said, well, that paper of yours from 2017, I'm not sure, are you sure of those predictions? I was like, well, yeah, I shouldn't be invested. I'm a scientist, I should be agnostic, but I'm kind of invested. I really believe they exist. And then he said, oh, wouldn't that be a dream? I said, oh yeah, that would be my ultimate dream right now. And he said, well, I have fulfilled your dream. I found the object. So he found an object that was discovered in James Webb, and one of the predictions was that it had to also be seen in X-rays by the Chandra X-ray telescope. So this object UHZ1 was found both in James Webb and in the X-ray, and it had the properties. And we had said that it would be kind of, this is all the quasars that have been found by the James Webb Space Telescope, their brightness and distance from us. And this one, is this purple one, it would be an outlier. We knew it would be a huge outlier, and it turns out that it satisfied all the properties. There were 6 properties that this source had to satisfy in order to be a direct collapse black hole candidate, right? And remember, this is very important. Even finding one object tells you that this process can happen in the universe, right? And that there have to be multiple ways to form black holes. On the right-hand side, I want you to look at the orange lines. That's the prediction. And what you see in the red is the detection. It's unbelievable how good the match is. Okay, it really was truly surprising, unanticipated that it would come so soon with James Webb data. And we were able to show from mapping out the growth history, starting out with a heavy seed, you could then comfortably produce this object that you see. And that you had to start with a heavy seed early on in time, and this is the time growth history of that black hole in that galaxy. And we had also predicted, as I said, there were many properties that it had to satisfy. Not just that it should be seen in James Webb and an X-ray, but there were very particular quantities regarding the shape of the spectrum that I just showed you, as well as the ratio, the amount of energy that's coming out in light in the infrared seen by JWST versus Chandra. And there you see, that was our prediction. Our prediction are these models in black, and the blue is the data. So, so this set of properties. So, I mean, this is just, I can't even tell you. I'm speechless. I was speechless then, and I'm speechless even when I talk about it now. It's just remarkable that today it is possible to be a scientist that within a lifetime, you can make a prediction, and it can actually be validated within your career, within a decade or two of your career. It's just, this is what's so beautiful about science, what the dizzying, sort of really dizzying pace of discovery right now. So the question is, so what is really interesting, that's in the very early universe. So that candidate, UHZ1 that we found, was when the universe was barely 500 million years old, right after the Big Bang. So it's telling you black holes form really fast, really early, and in multiple ways. So that one object has actually taught us so many different things. The question is, can this direct collapse happen at other places in the universe, other times? Maybe. And we have a potential candidate for later on in the universe. Maybe you can form. But what has been remarkable is that I have worked not just on these direct collapse black holes, but also in another way, yet another way, to make and amplify the masses of these seed, the first black holes. And that is nuclear star clusters. So these are clusters of stars, compact clusters of stars, about 100,000 to 1 million stars that form. They can form early in the universe. They also form late in the universe. And those regions can act as incubators for the formation of black holes. Because those stars will leave corpses. They will leave those black holes that they can all collide with each other and make a big black hole. Or, as we suggested earlier in 2014 in a paper, that you could have one star that has become a black hole, and then it's kind of bouncing around, colliding with all the other stars, but it's eating gas all the time, because these nuclear star clusters have a lot of gas. So it's growing, it becomes really massive, and it ends up in the center. And guess what? Dreams coming true again and again. So recently an object was discovered that satisfies this kind of scenario. So basically this tells you that nature makes black holes in multiple ways, right? So what comes next? Okay, so we are looking and we have some great insights into seeding and the formation of the first black holes. We understand how they grow. I think the thing that really we haven't done yet is to make a black hole in a simulation. We've not yet reached there. So that's the next kind of computational challenge for us. We see the gas getting condensed into a small region, but we have not yet, we don't have the resolution, both numerical, temporal, spatial, to be able to follow it and that collapse process to give you that really concentrated compact mass. So that's really the frontier with computation. Observationally, the hints for excitement are already in the air. So these collisions of supermassive black holes that I told you that we have not yet detected, the gravitational waves, we actually have seen a hint. We saw the waves generated by the collective collisions of supermassive black holes all across the universe by pulsar timing arrays. That was recently reported. So we see sort of first hints of that. That measurement, an actual detection and measurement, a credible one, is going to come very, very soon. So that's what's next. You know, and the next thing, for those of you who are into data science and AI and wondering, you know, what's all this fuss about? We hear about AI all the time. Is there any good that can come out of this? Turns out that AI can actually really amplify even further the pace of scientific discovery, because it allows us to do some really interesting things. So when I'm looking out into the universe, I'm looking for quasars. I preferentially find only the brightest things that are farthest away. If I want to know what your average quasar when the universe was a fraction of its current age looked like, I have no idea. What do I mean by average quasar? Well, I'm interested in the average black hole, but obviously it has to be a quasar for me to be able to see it and study it, right? So we can't do that. So we have to study populations, and we are seeing the tip of the iceberg. We are always seeing only the brightest guys. It's almost like, you know, you went to America, and the only people that you saw were the really, the tall people who were above 6 feet tall, and that you didn't see anyone else. And you would have a false view of what the heights of adults in America is, right? So that's the kind of thing that happens very classically in astronomy. You tend to see these outliers. They're not characteristic. So AI can help us there by helping us fill in. One of the things that AI can help us do is kind of fill in the populations that are more characteristic by training on a calculation that reproduces the brightest objects. It can help you fill in, right? And then we can compare that with data. Then we know where to go look for those objects, how to look for the objects that are actually fainter. So in all of this, one other really exciting possibility that has opened up, well, it was opened up by Stephen Hawking in 1974, but it's had a bit of a rebirth, is this idea of primordial black holes. That in the very early universe, just as the universe came to be, you formed these singularities. These punctures in space-time were there right at the very beginning, and that they grew over time, and they could have been the first black holes that seeded everything else that we see today. Doesn't quite work. That scenario, again, needs a lot of assumptions to be made at the moment, but it's looking like a very, very exciting possibility. So in terms of what's next, that's next. One of the other things that has been really cool, I'm trying to show you also sort of the process of discovery, the process of research, where you don't actually know if you're going to make a discovery. But then what you do is you take a complex problem, you pare it down, and you solve it, and you try to compare with the data. And if it doesn't work, you're like, okay, maybe I have not included everything that's needed, that's essential to this problem. So then you add a bell and a whistle, and then you redo, and then you compare with the universe, because the data is what you have to compare with to validate any scientific idea that you have. So one thing that was being done in computer simulations was that when these black holes, remember, they don't quite form, but when we place the black hole at the center of a galaxy, we used to pin it down and prevent it from moving, Because remember, it was artificially done anyway. It's not like the black hole is forming ab initio in the simulation. So a team of simulators realized that what if we don't actually pin that particle and allow it to move? Then what happens? What happens computationally, right? So it turns out something very interesting happens. It turns out that all those black holes that fall in and collide when the galaxy assembles, like I showed you of two galaxies colliding, they don't actually reach the center. Some of them don't make it all the way to the center. They're kind of hanging around and wandering. So that then reveals there could be a population of wandering black holes in galaxies. So this is from a simulation that shows you that the different kinds of galaxies could have all these dots that you see are wanderers. And guess what? Now that we know that we should be looking for black holes not just at the center, but off-center too, we're finding them. So it turns out that theory can inform data, and data, of course, is the ultimate arbiter of theories, right? So this is a case when in sort of fundamental black hole science, where theory was able to show that we need to start looking for black holes in different ways, and then we will uncover a completely new population. So this population of wanderers has actually been uncovered. So you might say, ultimately, like, what is my dream? Okay, which is the one thing that I would, now that, I feel pretty happy that the word from the universe is that black holes likely form in multiple ways. So, that quest is done. What is the next big thing that I'm personally most excited about? And that is this. So this is a European mission called LISA that we hope will fly in the 2030s. And it's an interferometer. It's sort of 3 satellites that are in tandem flying in space that will detect gravitational waves from colliding supermassive black holes. And there is so much information in supermassive black hole collisions that we have from the visible wavelengths. And these would be new waves, a completely new window in the universe. This is not light. These are actually gravitational waves. And for the case of supermassive black holes, then we have a new fantastic jigsaw puzzle where we have to put all of this together. We have to see and understand what happens, what are the fireworks that we can see that start to happen when 2 supermassive black holes get really close and ready to collide. We've made some progress there. We know what kind of fireworks to expect. And then what happens when they do collide? They produce those gravitational waves. And then what happens when they're sort of finally settling down and you have one much bigger black hole? I think all of those stages, putting all those stages together, for me, would be mapping out birth to death of a black hole. And for me, that's the biggest question that remains to be answered. Thank you so much for your attention.